This week has been pretty heavy with agricultural examples, and with good reason. These ideas around quantitative heritability form the theoretical basis for using selective breeding to improve traits in livestock and in crops. Here's how a selective breeding program like that might work, using a strategy called individual selection. Let's say you've got a heritable trait in a heterogeneous population. I don't know, the percentage of milk fat that a cow produces. Because the population is heterogeneous, you've got a distribution of individuals. Let's say that the mean of this distribution is M. Now, let's choose a cutoff point. Let's say that cutoff point is right here. And what we do is we form a subpopulation of individuals, and that subpopulation has a mean of M star, where M star, right, the mean of these individuals is greater than the mean of the overall population. So now, if we let the individuals in this selected subgroup breed together randomly, what does the distribution of progeny look like? Well, because this trait is heritable, it makes intuitive sense that the progeny would have a higher mean. The individuals above our cutoff point had more alleles on average that contribute to a higher milk fat. And so they pass those alleles on to their offspring who also produce milk with a higher milk fat. The cool thing about approaching heritability quantitatively is that we can actually predict the characteristics of this progeny population. And so if we know the narrow sense heritability of this trait, for example, by doing a correlation study like we talked about in the last video, then the progeny population mean, M prime, is the parent population mean, M, plus H squared times M star, right, which is the mean of our selected population minus M. And again, one way that this is useful is that it has predictive value, right? It can tell us how much improvement we expect to see for a given breeding program. The other way it's useful, though, is that it gives us another way to estimate this narrow sense probability, right? If we rearrange this equation to solve for little h squared, then our narrow sense heritability is M prime minus M over M star minus M. And so if we actually do this breeding experiment, the selective breeding experiment, to improve a trait, we can also use that information to estimate the narrow sense heritability of that trait as well. There are two other important points, though, to make about this kind of artificial selection. And the first is, can it continue forever? Not really. And there are two reasons for that. First, as artificial selection continues, alleles become fixed, right? The population basically becomes inbred, with the genes that affect the trait of interest becoming homozygous and fairly rapidly, not terribly many generations required, which means that the amount of genetic variability decreases steadily until eventually there isn't any left. And so remember that our definition of the narrow sense heritability is sigma squared A, right? The variance in phenotype due to differences in alleles over the entire phenotypic variance that we observe. And so, as all of those alleles become fixed, as this population of cows, say, becomes inbred, then the variance that is due to additive effects of different alleles approaches 0, which means our narrow sense heritability approaches 0, which, when we plug it back into this equation, leads to M prime, right? Our next generation's mean simply equaling M, our previous generation's mean, right? There aren't any more improvements possible if all of the alleles get fixed and there is no more additive variance. This is called the selection limit. It's the point at which further selection doesn't yield any more improvement in the population. The other reason that selection can't continue forever is because genes that have a positive impact on the trait of interest also have a negative impact on overall fitness. For example, the selection of body size in animals bred for meat often decreases their fertility as well. And so we say that this second trait has undergone a correlated response. And this is pretty typical in long-term artificial selection. Eventually, the selection for one trait, the trait of interest, is balanced out by the natural selection against it. And again, we've reached a selection limit beyond which no further improvement in this trait is possible. Before we leave individual selection, though, there's another context where it can aid our understanding of heritability, and that's inheritance of threshold traits in humans. And that's our next topic.